Dirichlet problem. I want to solve the potential when I have the potential, when I have the n at the boundary. It means that I have the geoid height. I have geoid height at the R. What does that mean? Well, for example, do we measure the geoid? Yes. We can say, for example, satellite altimetry. Satellite altimetry measures the distance from the satellite. Let me see. We have a satellite and this is C. This distance is measured. And it is in fact mean sea level plus sea surface topography. But sea surface topography is maximum 2 meters. And it's not that. It is some approximation. We can say that MSL is N. Means that what we obtain from satellite altimetry is approximately mean sea level. So if we have that, what will be the gravitational potential? What will be the disturbing potential if we have measured Ln? That's the question. How do we do that? So the general solution of the disturbing potential in terms of spherical harmonic is T for a point outside. I told you that you can expand any function with the spherical harmonics, R over M, N, sigma M minus N. I write T and M in this side. T and M is the spherical harmonic coefficient of the T, Y, and M. So, what do I have? I have N. What is the relation between N and T? I say N is T divided by gamma according to the Bruns formula. So that's simple. If I divide T by gamma, I get N. So the geoid can be determined directly by dividing the spherical harmonic expansion by gamma, the normal gravity field. So then you have the T and M, Y and M, theta and lambda. So now imagine that I have measured N and I want to determine T outside the Earth. And what I have is N at the surface of the sphere. So N at the surface I want T outside. So that's simple. If I can compute spherical harmonics of the M, you should remember the synthesis, the analysis. If I measure N all over the sphere, Y and M, theta prime, lambda prime, d sigma, and I get this Nm. If I insert Nm back to the spherical harmonic expansion for T, theta and lambda, sigma and infinity, R, n plus 1, this time. So I want to put here, see that Nn is T and M over gamma according to the Bruns formula. So if N is T over gamma, the harmonics of N will have the same relation with the spherical harmonics of the disturbing potential. So if I divide this, I can simply write that gamma multiplied by n, gamma multiplied by nmm ynm. So this one I have computed. I have derived the nm, that nm comes here. And if I put it here and simplify, I come to the Poisson integral. 4 pi will be, and I have the gamma outside, and then will be n at the surface, and I have Poisson kernel here. This part, do it as an assignment, drive that formula. Drive this. So you see that you have Poisson kernel here, contains all frequency, and if you measure the geoid even over this limited area, over oceans, you can generate the potential outside the geoid, outside the surface, from disturbing gravity disturbance to the geoid. So I have T. The first relation was Brun's formula, and this delta G was the derivative of T, the radial derivative of T with. So the goal is that if I measure gravity disturbance, I can generate the geoid from gravity disturbance. So how can I do that? So that's quite simple. T we have, the spherical harmonic of T, we have T there. Then if I write this delta G, for example, T is here. We write the relation for that. Let me see, delta G. So this is the spherical harmonic expansion of the gravitational gravity disturbance. That's the spherical harmonic gravity disturbance. And if I determine this one, and this, and for this n, I already have this the gravity expansion. So if I make this equal R equal to R, for example, then delta G at the surface So from this equation, it is simple to conclude that if I take away the summations, so I already have the formula for the geoid, if you remember. It was 1 over gamma. So that's interesting. This comes here. If this comes here, then I can make an equation which connects the geoid directly to the spherical harmonics of the gravity disturbance. will be R over R sigma self infinity. Now I want to make an integral equation for that. Delta G and M already, I can define it in a spectral form like that. That if I put them here, 1 over. So what do you see here? Here. It's addition theorem. This will be 2m plus 1 pn cosinus psi. That's all. Then n will be all. Yeah. You can determine the geoid directly from the gravity disturbance. This formula here is known as Haughton's formula. And there has been lots of efforts and works you will find on the internet to determine the geoid using Haughton formula. And this kernel, which is written in by H, is called Haughton kernel. Haughton kernel. Then you have the gravity disturbance. Then you can determine the geoid. That's the boundary value problem of Neumann type. Then you have the derivative.